Okay, so we are talking about network flow network. So just to recap, in the last class we have started this topic. So a network graph, a flow graph is a graph, is a directed graph. So where we have a source node S and we have a sink node T, and each node, each edges are associated with some capacity. This is the capacity. Okay, so these are the capacity basically of each edge. So if there is no edge between any two vertices, then the capacity will be 0. Okay, so then this is the flow. Now we want to, this is the positive flow. Positive flow. So in the last class we defined the positive flow. It is a we want to flow some current from source to sink, so that in the intermediate vertex there will be no consumption of the current. So that means it is a function from, it is a positive flow, it is a function from V cross V to R such that is satisfy few conditions. Like first condition is the flow, positive flow should not be greater than the capacity. So P of u v must be less than equal to C of u v for all u v belongs to E, and we have seen the flow conservation. That means if we take a vertex u, so the flow coming into this vertex and flow going in from this vertex, this sum should be same. So that means summation of P u v. So this is flow going out, V belongs to V minus u minus summation of P V u, V belongs to V, this should be 0. So that means no flow consumption should be there. So this is called this is one of the property, this is called flow consumption. Okay, then the value of the flow we define. So the value of the flow is basically the flow which is going out from the source, and this is true for this flow consumption property is true for all u which is not source and sink, but for source and sink we are passing the current from the source and sink is receiving the current sort of. So this is the value of the flow. Value of the flow is basically the effective flow, effective current we are passing from S. So that is basically summation of P S comma V. This is for all V belongs to V minus summation of P V comma S. This is the value of the flow. So this same amount of flow we are is going to the sink also. Okay. So now we have seen another concept which is called flow cancellation. So that is like if we have a vertex, say from this to vertex u to v. So there is a flow 2 amount to, this is positive flow, 2 is going there, 1 is coming here. So instead of that, if we just make it 0, so effective flow is, this is called net flow, we define the net flow. So effective flow is, we can make it 0, we can make it 1. So this is the effective flow from u to v. So this is basically flow cancellation. So this is basically without loss of generative, we can assume that flow is going to only one direction. So either from u to v or from v to u. So if there is two direction, we will just cancelling the flow and we will take the net flow. So that is the concept. So let us define the net flow. So net flow. So this is the definition of net flow. So basically net flow is a function F from V cross V to R such that it satisfies three conditions. Again the same capacity constant, say for u v. So, it should be less than C of u v for all u v belongs to E. So, net flow should be less than the capacity, and flow consumption is 0 at every point, because every point has effective flow is 0. So, that we have to write. So, for all u which is basically coming from this set, we have summation of f of u v is basically 0. This v is belongs to this. So, here we have one sum. In the positive flow we are having two sum, but here we have one sum because we are just considering the net flow. We are doing the flow cancellation if there is both side flow. So, this is the flow consumption, flow conservation property, and another property is called Q symmetricity. This is the new one, Q symmetric property. This is telling, so suppose there are two vertex u to v. So, if there is a flow from f from u to v, then there is a flow, then there is a negative flow from v to u. This is the symmetric skew symmetric property. So, that means f of u v is equal to minus of f of v u for all u v belongs to v. So, that means if there is a flow, then from reverse direction it is minus of that. So, effective flow. So, if we say for example, for this vertex, for this is u, this is v. So, there is a effective flow from u to v is 1. So, what is the flow from, if this is 1 unit flow is going from, this is the effective flow, net flow. Then what do we say, what we can say, from this to this we have minus 1 flow is going, something like that. So, this is the skew symmetric property of this. Now, this is the definition of the net flow, and we already have a definition of the positive flow. Now, we will see these two definitions are equivalent. So, how to get that? So, we want to see these two definitions are equivalent, positive flow and the net flow. If we have given a positive flow, we can have, we basically have a net flow. If we have a net flow, we can have a positive flow. So, this is called equivalence of two definitions. One is net flow, another one is positive flow. Okay, so first one, suppose we have a graph, we have graphs net, we have a flow graph. Now, suppose we have a positive flow P. Okay, suppose we have a positive flow on this graph. Now, we have to have a net flow. So, how to define the net flow? So, we just define f of u v is basically p of u v minus p of v u. So, that means if there is two vertex u to v, so this is basically p of u v, this is basically p of v u. Now, the net flow is, we define this net flow by this way. Now, we can easily see, so this is a function from v cross v to r. Now, we can easily see, we can easily verify this is a net flow function, because we can see this is satisfying three conditions like capacity constant. So, this is basically f of u v is less than C of u v, because this is anyway less than the capacity, and we are subtracting some quantity if this is greater than equal to 0. So, this is true, and another property is the flow conservation property. So, that means, if you take a vertex V from this which is not source or sink, then we want to calculate summation of u comma v. V is basically summation of, this is say u comma v. This is basically nothing, this we want to show it to be 0. This is nothing but summation of this, summation of p u comma v minus summation of p v comma u. So, this is all v and this is all v. Now, we know this is 0 from the definition of the positive flow. This is the positive flow. We have given a positive flow function, then we defined a function like this, and this function is a net flow function. Now, we want to see the Q symmetric. So, if we have a so Q symmetric property means the value flow value from u to v is basically negative of. So, we have u and we have v. So, if this is the third property. So, what is the flow value from u to v? So, this is basically, so f of u v is basically how we define p of u v minus p of u. So, this we can take minus of p of v u minus p of u v. So, this is nothing but, by this definition, this is nothing but minus of f of v comma u. So, this is the Q symmetric property. So, these three properties are satisfying. So, this is a so this is nothing but a net flow. So, now we want to show, if we have given a net flow, how we can get a positive flow. So, that is the other way around. Suppose we have given a net flow, say then suppose if this is a net flow function. So, this is a net flow. Now, if this is a net flow, now the question is how we can have a positive flow function. So, we define like this, p of u v is, because positive flow is always positive. So, we define this f of u v, if it is 0, if it is positive, otherwise it is 0 if f of u v is less than 0. Okay. So, that means, so if we have two vertex u v, there if there is a flow f, now if f is positive, then that is our p of u v. But if f is negative, then we do not have, then p of u v is 0 basically. So, that is the way we define this. Now, the question is how to prove this is a positive flow. So, for positive flow we have to again show the condition like capacity constant. So, this is trivial because p of u v is not either 0 or this, and both are basically less than c of u v, because capacity, if there is no edge, then the capacity is 0, no edge between a two vertex u v, otherwise it is the positive. Okay. And the second one is basically we need to show flow conservation. So, for flow conservation what we need to do? So, so if this is greater than 0, then we know p of u v minus P of V u. This is basically f of u v, because in that case this is 0, this is 0, because this is positive, means this is P of u v is this one, and minus of that is negative. So, that is 0. So, this is okay. So, now if this is less than, if P of u v is less than 0, then we have, that is minus, we have P of u v minus P of v u is basically minus of this. Okay. So, this is basically by the Q symmetric property. Now, therefore, if you take the sum, like summation of P of u v, this v is varying from v minus summation of P of v u. So, this is nothing but summation of f of u v, and this we know, this is nothing but f of u v, this we know 0, because net flow consumption at any point is 0. This we have already, this is coming from the definition of net flow. Okay. So, these two definitions are basically equivalent. So, given a net flow, given a positive flow, we can have a net flow. Given a net flow, you can always think of a positive flow. Okay. So, now we will deal with the net flow, because it is the simplified notation. Instead of both the direction, we have the net flow, effective flow. So, that is the basically simplification in the notation. So, we will deal with the net flow. Good. So, now suppose we have a net flow, then how we will define the value of the flow? So, this is another definition. The value of the flow, the value of a flow f is denoted by and it is basically given by summation of f of s comma v, and this v is coming from v. So, this is basically in Z, it is we denote by this. Okay. So, this is basically the net flow. So, we have a source vertex S. So, we have other vertices over here. So, net flow, we are just talking about net flow, we are not talking about positive flow. In that case, there will be a flow from this side. So, we are just considering the one side flow, that is the effective flow or the net flow. So, that way, so we just sum. So, these are the net flow. So, we sum all of this net flow, and that will give us basically summation of f of s comma v this. So, this is the flow we pass from the source to the sink. Okay. And then, so yeah, so that is the thing. So, now this is the set theoretic notation f of s comma v. So, similarly we can, I mean the flow consumption. So, if we take a vertex v, so the flow consumption is basically on this vertex is 0. So, how we define that? So, that is basically in terms of net flow f of u comma v is 0. So, this is basically in Z notation, this is basically flow. So, this is nothing but summation of s of u comma v. So, this is in Z notation. So, this is 0. So, this is basically the flow consumption at any node is 0. Now, we will have some properties of this, properties on this net flow, some properties of flow. especially net flow. We are talking about now our flow is net flow. So, we have given a f, we want to talk about some properties of f. Okay, the first lemma, first property of f of x comma x is 0, where x is a set. So, here we are dealing with the set. Okay, so how to show this? How to prove this? So, how to prove this? S of s comma s is 0. So, to prove this, suppose what is s of s comma s? So, this is basically double sum. So, this is s is a subset of V. So, S is a subset of V, it contains some of the vertices, S is a subset of V. So, basically this is nothing but summation of double summation of f of u v. Now, u is belongs to x and v is belongs to x, both are belongs to x. Okay. So, now this we can write as summation of f of u comma x. So, basically, so this is basically the net flow which are going from s to s. So, this is nothing but 0, because we know the net flow of any vertices is 0. So, sorry, this is basically coming from double summation. Now, we take the sum of this. So, this is basically summation of u belongs to x f of u comma x. Okay. So, now this is all the flow from x to that vertex. So, this is basically will be same as, so this is net flow will be same as all the flow which are outgoing from this vertex. So, this is basically the 0. So, net flow is basically 0. So, this property is okay. Now, we have, so how we are doing? Yeah, so we have to be fast. So, this is basically another property f of x comma y, basically minus of y comma x. So, this is basically coming from q symmetric property of the net flow. Then the another property is basically this is minus f of x comma y comma z is nothing but, so these two are disjoint set x comma z plus f of y comma z, where x y are disjoint set. Okay. So, this is the property we have. So, where x y are disjoint set. So, how to prove this third property? Because say this is x is a x or y all subset of V basically. So, how to prove this? This to prove is, so if we have a disjoint subset, so basically it is coming from, so we just we just take the sum. So, this is what? This is nothing but summation of double summation of f of u comma v, where u belongs to and v belongs to z. Okay. Now, u belongs to this means it is basically disjoint set. So, it is basically we can write this sum as summation of u belongs to x, v belongs to z, f plus summation of u belongs to y, v belongs to z, v belongs to z, f. So, this is nothing but f of x comma z plus f of y comma z, and this is true because they are disjoint set. Okay. So, now we will use this result or this theorem or this lemmas to prove another theorem, which is basically called which is basically telling us the flow, I mean the net flow, the flow of a network. So, that we will discuss. They will start from here in the next class. Thank you.